Picture yourself standing at the edge of human knowledge, staring into the cosmic abyss, where something impossible is unfolding. Every telescope on Earth that can see it is pointed skyward. Every astronomer who knows about it is watching, and what they're seeing shouldn't exist. Not here, not now, not according to the rules we thought we understood about how the universe works. This is 3I ATS, and it's rewriting the textbook on comets faster than we can turn the pages. The story begins on July 1st, 2025, when a telescope in Chile caught something moving against the backdrop of stars. The asteroid terrestrial Impact Last Alert System, ATLAS for short, spotted an object entering our inner solar system at a distance of 4.5 astronomical units from the Sun. That's about 420 million miles, a region of space where comets typically sleep. They're cold, dormant, silent. This one was screaming. Within hours, follow-up observations started pouring in. Professional astronomers, amateur sky watchers, everyone who could point a telescope at the designated coordinates saw the same thing. A fuzzy object with a coma, that telltale cloud of gas and dust that makes comets look soft and diffuse instead of sharp like asteroids. But there was something else in those first images, something that made veteran comet hunters pause and look twice. This wasn't just another ice ball wandering through our neighborhood. The orbital calculations came back quickly. Too quickly, perhaps, for anyone's comfort. The numbers were unambiguous. This object was moving at 61 kilometers per second relative to the Sun. That's 140,000 miles per hour. That's not fast for an interstellar visitor. It's impossibly fast. Our solar system's comets don't move like that. They can't. They're bound to the Sun's gravity, trapped in elliptical orbits that bring them back again and again over thousands or millions of years. 3I ATS isn't coming back. Its orbital eccentricity, measured at 6.14, an astronomical measure that tells us the shape of an object's path through space. Anything below 1 means you're in an ellipse, forever circling. Anything above 1 means you're on a hyperbolic trajectory. A one-way ticket through our cosmic neighborhood. 6.14 doesn't just mean this comet is leaving. It means this comet was never ours to begin with. It came from somewhere else, from some other star's family, carrying the chemical signatures and physical properties of a solar system we'll never see. This is the third confirmed interstellar object ever detected passing through our solar system. The third visitor from the vast darkness between stars. The third messenger from stellar systems billions of miles away, each one teaching us that our solar system is not alone, not isolated. Not the only factory in the galaxy churning out worlds and comets and the building blocks of life. The first was Oumuamua, discovered in October 2017. That one looked like nothing we'd ever seen. A cigar-shaped tumbler that some said resembled an alien spacecraft. It was dry, showing no signs of outgassing, no coma, no tail. Just a mysterious rock speeding through our solar system faster than anything that belonged here, accelerating in ways that sparked endless speculation and controversy. We barely got a look at it before it vanished back into interstellar space, leaving us with more questions than answers. The second was 2I Borisov, discovered in August 2019. This one behaved exactly like our comets do. It had a coma, it had a tail. It outgassed water and carbon monoxide in amounts that made perfect sense for a comet of its size at its distance from the Sun. It was predictable. It was boring in the best possible way, showing us that comet formation must work roughly the same way in other star systems as it does in ours. We could study it, understand it, fit it neatly into our models of how planetary systems form and evolve. 3I ATLAS is neither of those things. On July 2nd, 2025, the Minor Planet Center made it official. This object had earned the designation 3I, marking it as the third confirmed interstellar visitor. They also gave it the cometary designation, SEED 2025 N1, recognizing its active coma and confirming what everyone watching already knew. This was a comet, an icy body shedding gas and dust as the sun's heat worked on its surface. But what kind of comet? What kind of rules was it following? Those were questions that would take months to answer, and with each passing day, each new observation, the mystery only deepened. The trajectory itself raised eyebrows immediately. 3I, Atlas came into our solar system from the southern celestial hemisphere, from a direction near Sagittarius, near the Milky Way's galactic center. That was unexpected. Most astronomers had predicted that interstellar objects should come from the solar apex in the north, the direction our sun is moving relative to nearby stars. That's where you'd expect to run into things, the way bugs hit your windshield when you're driving down the highway. But 3I, Atlas came from behind us, from the opposite direction, suggesting either it's a rare discovery or our assumptions about interstellar object populations are wrong. And here's where it gets really strange. The comet's trajectory is aligned almost perfectly with our solar system's orbital plane, the ecliptic. It's tilted only 5 degrees from the flat disk, where all our planets orbit. Think about how unlikely that is. Space is 3-dimensional. An object coming from interstellar space could arrive from any direction, from above, from below, from the side, from any angle across the full sphere of possible trajectories. But 3I, Atlas came in almost flat with our solar system's plane. Like it knew where the planets would be, like it was following a predetermined path. Some people immediately started whispering about directed trajectories, about probes, about artificial objects sent to investigate our solar system. One prominent astrophysicist even published a paper suggesting 3I, Atlas could be an extraterrestrial spacecraft, pointing to its seemingly anomalous characteristics as evidence. The overwhelming consensus among astronomers was immediate and harsh. No, this is a comet. It's showing all the classical signatures of cometary activity. It's just an unusual comet, probably, maybe. But the whispers didn't stop. Because let's be honest, when something this weird shows up, when something behaves in ways we can't immediately explain, the human mind goes to interesting places. The truth, as always, is probably stranger than fiction, but not in the way we expect. Let's talk about what 3I, Atlas is doing that has every astronomer who studies comets absolutely riveted. Let's talk about the water. In early 2025, NASA's Swift Space Telescope turned its ultraviolet eyes toward 3I, Atlas. Swift was designed to hunt gamma-ray bursts, the most violent explosions in the universe, but it's also excellent at detecting the ultraviolet signatures of molecules in space. And when Swift looked at 3I, Atlas in late July and early August, it saw something that shouldn't be there. A halo of hydroxyl molecules, OH, surrounding the comet like a ghostly shroud. Hydroxyl is what you get when sunlight tears water molecules apart. UV photons hit H2O, break the bonds between hydrogen and oxygen, and you're left with OH radicals fluorescing in ultraviolet light. When you see OH around a comet, you know water was just there. It's the echo of water dying. The forensic evidence that tells you water molecules are escaping from the comet's surface and being destroyed by the very sunlight that freed them. Swift saw a lot of it, an enormous amount of it, enough to calculate that 3I, Atlas was releasing 1.35 times 10 to the 27th water molecules every second. Let me put that in terms that make sense. That's 40 kilograms of water every single second, 88 pounds per second. The equivalent of a fire hose running at full blast, continuously, out in the cold vacuum of space, where fire hoses have no business running. At a distance of 3.51 astronomical units from the Sun. That's 325 million miles. That's more than 3 times farther from the Sun than Earth is. Out there, sunlight is weak. It's a whisper. It's barely enough to warm the surface of an icy comet. Certainly not enough to drive the kind of water outgassing we'd expect from, say, a comet passing near Earth's orbit. Our solar system's comets don't do this. Not out here. They wait until they're much closer to the Sun. Until they're inside Mars' orbit. Until the solar heating is strong enough to really get things moving. Then they wake up. Then they start streaming water vapor into space. but not at 3.5 AU. Never at 3.5 AU. 3I ATS didn't get that memo. 3I ATS was already hemorrhaging water into the void when it was 6.4 astronomical units from the Sun, according to observations from NASA's Transiting Exoplanet Survey satellite. Back in May 2025, 2 months before anyone even knew this comet existed, TESS caught it on camera as part of its exoplanet hunting mission. The images show clear cometary activity, a brightening, a coma already forming. That's almost 400 million miles from the Sun. That's out in the realm where water should be frozen solid, where icy surfaces should be stable, where nothing should be happening. But something was happening. Something is still happening. The question that keeps astronomers up at night is simple and terrifying in its implications. How? What mechanism could possibly drive this level of water outgassing at these distances? What kind of comet behaves like this? Let's consider the possibilities, because that's all we have right now. Possibilities. Theories. Educated guesses based on decades of studying comets that apparently don't apply here. First possibility, exotic ices. Maybe 3I ATS isn't primarily water ice. Maybe it contains large amounts of super, volatile materials, ices that sublimate at much lower temperatures than water. Things like carbon monoxide, carbon dioxide, methane, nitrogen. These substances turn from solid to gas at temperatures far below water's sublimation point. If 3I ATLAS has a lot of these super, volatiles mixed in with its water ice, the outgassing of CO or CO2 could be lifting water ice grains off the surface, carrying them away from the nucleus, where they subsequently sublimate in space. The water vapor we're seeing might not be coming directly from the surface at all, but from tiny ice particles floating in the coma, melting in the thin sunlight. The James Webb Space Telescope, JWST, confirmed this in August 2025 when it turned its powerful near-infrared instruments toward 3I ATLAS. What it saw was remarkable. The comet's coma is unusually rich in carbon dioxide, extraordinarily rich. The CO2 to water mixing ratio measured at 8:1. 8 parts carbon dioxide for every 1 part water. That's one of the highest carbon dioxide abundances ever seen in a comet, especially at 3.32 astronomical units from the Sun where JWST observed it. Most solar system comets show the opposite pattern. They're water-dominated, with carbon dioxide as a minor component. And even when you do find carbon dioxide-rich comets, they follow a predictable trend. The farther from the Sun, the higher the ratio of carbon dioxide to water, because carbon dioxide sublimes more easily than water at greater distances. But 3I ATLAS breaks that trend spectacularly. At its distance from the Sun, it should have maybe a 2:1 or 3:1 ratio. 8:1 is off the charts. The only other comet that comes close is C2016 R2 Panstaras, an Oort cloud comet that also showed bizarrely high carbon dioxide levels and left astronomers scratching their heads. What does this tell us? It tells us 3I ATLAS formed in a very carbon dioxide-rich environment. Either its parent star had an unusual protoplanetary disk, with more carbon dioxide than we typically see, or 3I ATLAS formed very far from its parent star, beyond the carbon dioxide frost line, where temperatures were cold enough for carbon dioxide to condense into solid ice. Or, and this is the hypothesis that makes my skin crawl with excitement, 3I ATLAS might have a thick, insulating crust hiding water ice underneath. The crust could be making it difficult for water to escape, while carbon dioxide, which sublimes more easily, is finding its way through cracks and pores, dominating the outgassing we observe. We won't know which scenario is correct until we get more observations, particularly after 3I ATLAS passes perihelion in late October 2025, when it's closer to the Sun, more active, heating up more significantly. We'll see if the water to carbon dioxide ratio changes. If it does, that tells us one thing. If it stays the same, that tells us something else. Every data point is a clue, every spectrum a piece of the puzzle. But carbon dioxide isn't the whole story. JWST also detected carbon monoxide and something called carbonyl sulfide, OCS, in 3I Aetios's coma. These are volatiles we expect in comets, but again, the ratios are interesting. The carbon monoxide to water ratio came in at 1.4 to 1, which is actually pretty typical for comets. So 3I Aetios isn't universally bizarre in its composition, just specifically weird when it comes to carbon dioxide. That specificity means something. It's telling us something about where this comet came from, about the conditions in its birth environment billions of years ago. And that brings us to one of the most profound questions about 3I Aetios. How old is this thing? A team of researchers led by Matthew Hopkins published a study in July 2025 attempting to answer that question. They looked at 3I Aetios's velocity components in the galactic coordinate system, breaking down its motion relative to the Milky Way's structure. They found that 3I Aetios is moving away from the galactic center with a velocity of 51 kilometers per second, and it's moving upward through the galactic plane with a velocity of 18.5 kilometers per second. That vertical velocity is quite high compared to nearby stars and other interstellar objects. What does that mean? It means 3I Aetios's orbit around the Milky Way is tilted. It doesn't stay in the galactic plane like most young stars do. It dips above and below, following a path more consistent with older stellar populations. Specifically, it suggests 3I Aetios belongs to either the thin disk or the thick disk of the Milky Way. The thick disk is composed of older stars that formed when the galaxy was young, when the interstellar medium had lower levels of heavy elements than it does now. Based on the typical ages of thick disk stars, Hopkins and his collaborators estimated, with 68% confidence, that 3I Aetios is between 7.6 and 14 billion years old. Read that again. 7.6 to 14 billion years old. The universe itself is only 13.8 billion years old. 3I Aetios might have formed when the Milky Way was young, when our solar system didn't exist, when the sun was nothing but a cloud of gas waiting to collapse. This comet could be older than Earth, older than Jupiter, older than everything in our stellar neighborhood. It's possibly the oldest comet ever seen by human eyes. An independent analysis by Asta Taylor and Daryl Seligman came to a similar conclusion, estimating 3I Aetios at 3 to 11 billion years old. Still ancient. Still a relic from a time when the galaxy looked very different than it does today. Think about what that means. This comet has been wandering through interstellar space for billions of years. It formed around a star we'll never identify, in a planetary system that might not even exist anymore. It was ejected from that system, maybe by a close encounter with a giant planet, maybe by a gravitational interaction with a passing star, and then it just traveled, for eons, for timescales that dwarf human comprehension. It passed through nebulae. It survived close encounters with other stars. A September 2025 study found that 3I Aetios may have passed within 3.3 light years of 25 known stars in the past 10 million years alone. Imagine the radiation it was exposed to, the cosmic rays, the gravitational nudges that slightly altered its trajectory, the slow, patient journey through the void, carrying chemical signatures from a protoplanetary disk that formed when your ancestors were single-celled organisms in ancient seas. If you have ancestors that old, maybe life on Earth didn't even exist when this comet formed, and now it's here, in our solar system. For a brief moment in cosmic time, maybe a year or two, we get to study it. We get to point our best telescopes at it and ask questions about where it came from, what it's made of, what secrets it carries about star formation and planet formation and the distribution of life, building molecules throughout the galaxy. We'd better ask good questions because we won't get another chance. Once 3I Aetios passes through our solar system, it's gone forever, accelerating back toward interstellar space at 58 kilometers per second, bound for destinations we can only guess at. Maybe in another billion years it'll visit some other solar system. Maybe some other species will see it and wonder, But right now, it's ours to study. And what we're learning is fundamentally disturbing. Let's talk about the cyanide and the nickel. Because if the water outgassing and the carbon dioxide abundance weren't enough, 3I, Atlas is also leaking chemicals that make you stop and think carefully about what you're looking at. On August 22nd, 2025, astronomers at Lowell Observatory reported the first tentative detection of cyanide emission from 3I, Atlas, cyanide, CN. The stuff of spy thrillers and murder mysteries, a deadly poison here on Earth, a fairly common molecule in space. We see it in comets all the time. It forms when complex organic molecules break down under ultraviolet radiation. It's not unusual. What was unusual was that they detected it relatively late, after nickel had already been spotted in the comet's coma. The Very Large Telescope in Charles confirmed the cyanide detection on August 21st and also found something else. Atomic nickel vapor, nickel-1, a heavy metal floating in the coma of a comet, glowing in the light of the distant sun. Now, nickel in comets isn't unheard of. We've seen it before in various solar system comets, including the previous interstellar comet 2I, Borisov. What's strange about 3I, Aetios, is the nickel is there, strong and obvious, but iron isn't. Usually, when you see nickel outgassing from a comet, you see iron too. They typically come in roughly equal amounts, part of the same processes that release metals from cometary material. But the Very Large Telescope looked for iron and found nothing. No iron 1 emission. Just nickel. Lots of nickel.
Why? How? Nobody knows.
The researchers who studied this, led by Rohan Rajagonkar, proposed several possibilities involving the chemical decomposition of nickel, containing organic compounds. Maybe there's nickel tetracarbonyl in 3I, Aetios, a highly unstable molecule that breaks down under radiation to release nickel atoms. Maybe there are other organometallic compounds we haven't considered. Maybe the space weathering this comet has experienced over billions of years has created a surface chemistry we've never encountered before. Maybe the parent star of 3I, Atlas, had unusual elemental abundances, enriching its protoplanetary disk in nickel but not iron. Maybe. The concentrations of nickel and cyanide increased steadily throughout July and August 2025 as 3I, Atlas, approached the Sun. By late August, the comet was releasing about 4.6 grams of nickel per second and about 17.6 grams of cyanide per second. Those are actually normal amounts for a comet of its size at its distance from the Sun. It's not spewing unusually large quantities of these chemicals. What's unusual is the ratios, the presence of one without the other, the timing of the detections. It's another piece of the puzzle that doesn't quite fit the standard model. And then there's what the Very Large Telescope didn't find. No atomic oxygen, no dicarbon or tricarbon, those carbon chain molecules that are common in solar system comets, no amino radicals. The MDM Observatory confirmed the absence of carbon chain compounds in August, revealing that 3I, Atlas, is one of the most carbon chain depleted comets ever observed. Its carbon 2 to CN ratio is off the charts in the opposite direction from most comets. It's not producing those molecules, or if it is, it's producing them in such small quantities that our telescopes can't see them. What does it mean when a comet doesn't make the chemicals we expect? What does it tell us about its formation environment, its thermal history, its exposure to radiation over billions of years? These are questions we're only beginning to ask, let alone answer. The coma itself is fascinating. High-resolution images from Hubble Space Telescope in July 2025 showed 3I, Atlas, surrounded by a slightly elliptical cloud of dust and gas spanning about 26,000 by 24,000 kilometers. That's roughly twice Earth's diameter, a substantial but not enormous coma for an active comet. The coma is reddish in color, similar to the hue we see in D-type asteroids and the previous interstellar comet 2I, Borisov. That reddish color probably comes from tholins, complex organic molecules that form when simpler compounds are exposed to ultraviolet radiation and cosmic rays over long periods. Tholins are the stuff of prebiotic chemistry, the building blocks that might eventually lead to amino acids and nucleotides, and all the molecular machinery of life. Seeing them in 3i, ATLAS tells us this comet is carrying the ingredients for life. Not life itself, but the ingredients, the recipe, the raw materials. Spectroscopy reveals that 3i ATLAS is ejecting small dust grains at high speeds, about 22 meters per second, and larger grains at slower speeds of about 2 meters per second. The dust production rate in July was estimated at 6 kilograms per second for small particles and 60 kilograms per second for large particles. That's similar to what 2i Borisov was doing when it entered our solar system, but lower than typical Jupiter family comets at similar distances. 3i ATLAS is active, but not spectacularly so. It's not a great comet, not something that will light up the sky and make headlines in general interest newspapers. It's faint, magnitude 13, or so at its brightest, requiring substantial telescopes to even see. But what it lacks in visual spectacle, it makes up for in scientific intrigue. The shape of the coma changed over time, and this is where things get really interesting from a physical perspective. In July and August, the coma appeared elongated toward the sun, not away from it like a tail. This confused people at first. Comet tails point away from the sun, pushed by solar radiation pressure and the solar wind. That's basic comet physics. But 3i ATLAS had a feature pointing toward the sun. A sunward elongation that didn't make sense until astronomers realized what they were seeing. It's not a tail, it's a dust plume. It's material being ejected from the sun, facing side of the comet's nucleus, where ice sublimation is happening faster, because that's the side getting direct sunlight. The nucleus of 3i ATLAS is probably rotating, and as it rotates, different parts of the surface face the sun and heat up, and start outgassing more vigorously. We're seeing an asymmetric jet, a directional emission, the comet breathing toward the star that's warming it. By late August, that sunward plume was still there, but 3i ATLAS had also developed a proper anti-solar tail. The comet now had both features: a sun, facing dust plume, and a sun-pointing tail. It was starting to look more traditionally cometary as its activity increased. Gemini South Telescope images from August 27th showed a tail extending about 30 arcseconds in angular length, roughly 56,000 kilometers. Still not massive by comet standards, but growing, evolving, showing us that 3i ATLAS is responding to solar heating in ways that make sense once you understand what you're looking at. What about the nucleus itself, the solid body at the heart of all this activity? We can't see it directly. It's hidden inside the coma, surrounded by dust that reflects sunlight and makes the nucleus appear larger and brighter than it actually is. But Hubble's high-resolution images from July allowed astronomers to set constraints. The diameter of 3i ATLAS's nucleus is somewhere between 320 meters and 5.6 kilometers. Most likely, it's at the lower end of that range, probably less than a kilometer across. That would make it similar in size to 2i Borisov, which had a nucleus about a kilometer in diameter, a kilometer-wide comet. Think about that. Something the size of a small mountain, tumbling through interstellar space for billions of years, finally passing through our solar system, just as we happen to have the technology to study it. If 3i ATLAS had arrived 100 years ago, we would have missed it entirely. 1,000 years ago, nobody would have known it was there. We live in the first generation of humans, with telescopes powerful enough to see these visitors, with instruments sensitive enough to analyze their composition, with the knowledge to understand what we're looking at. And we're still barely scratching the surface. The rotation period of 3i ATLAS's nucleus was measured at about 16 to 17 hours by multiple studies in July and August. That's the time it takes for the nucleus to spin once. We know this from watching the comet's brightness vary periodically, as the irregularly shaped nucleus presents different surfaces to our view. Except the variations are damped by the coma, harder to see than they would be for a bare asteroid. so there's uncertainty in the measurements. But 16 hours or so seems right. That's actually pretty typical for a comet nucleus. Not remarkably fast, not unusually slow. Just a solid, rotating, outgassing chunk of ancient ice and rock and metal and organics, following the laws of physics as it tumbles through space. One study in August tried to figure out which way the rotation axis points by analyzing the shape of the coma in Hubble images. They suggested the north pole of 3I, Atlas, might point toward either right ascension 154 degrees, declination plus 25 degrees, or right ascension 334 degrees, declination minus 25 degrees. Two possibilities. Two orientations. We'll need more observations to figure out which one is correct, and even then, the uncertainty is large because the nucleus is obscured. We're making educated guesses based on the distribution of dust in the coma, which is an indirect way to study the nucleus at best. Here's what keeps me up at night, though. Here's the question that nags at the back of my mind every time I read another paper about 3I ATIS. Are we seeing something genuinely anomalous? Or are we seeing something normal that just looks weird because we've never encountered it before? Our sample size for interstellar objects is 3. 3 visitors, 3 data points. That's not enough to establish trends. That's not enough to say what's typical and what's not. Oumuamua was dry and strange. 2I Borisov was cometary and normal. 3I Atlas is cometary and strange. What does that tell us? Maybe 1 out of 3 interstellar objects acts weird. Maybe we just got lucky catching the weird one. Maybe they're all weird in different ways. And we're only now starting to understand that our solar system's comets are the exception, not the rule. Maybe every star system makes comets slightly differently, with slightly different compositions and slightly different behaviors. And we've been spoiled by having 4.6 billion years of observations of our own comets to make us think we understood the rules. We don't understand the rules. We're still learning. And 3I Atlas is an excellent teacher, if a harsh one, showing us all the ways our models break down when confronted with something genuinely alien. Let's talk about what's going to happen next, because the story of 3I ATIS is still unfolding. Right now, as I write this, as you read this, the comet is approaching perihelion. That's the point in its trajectory where it comes closest to the Sun. For 3I Atlas, perihelion occurs on October 29, 2025, at 1.36 astronomical units from the Sun. That's between the orbits of Earth and Mars, about 126 million miles from the Sun. Not particularly close by comet standards. Many comets graze the Sun, passing within a few million miles or even closer, in some cases diving straight into the solar atmosphere and vaporizing. 3I Atlas won't get anywhere near that close. Its perihelion is actually farther from the Sun than Earth is. It's a fairly distant perihelion for an active comet, which makes its current activity level all the more remarkable. As it approaches perihelion, 3I Atlas will heat up more. The solar radiation will intensify. The sublimation rates will increase. The comet will become more active, producing more dust, more gas, larger coma, longer tail. Or at least, that's what we expect based on how our comets behave. Will 3I ATIS follow those expectations? Maybe. Maybe not. We'll see. There's also the possibility of outbursts. Comets sometimes suddenly release large amounts of material, brightening dramatically over the course of hours or days. These outbursts can happen when pockets of volatile ices beneath the surface suddenly get exposed and sublimate all at once, or when structural weaknesses in the nucleus cause chunks of material to break off. 2I Borisov experienced a fragmentation event during its pass through our solar system, the nucleus breaking into pieces, probably due to thermal stress or tidal forces, or the release of internal pressure. Will 3I Atlas fragment? It's possible. The nucleus is small, possibly fragile, definitely under stress from outgassing. Every time material leaves the surface, it changes the distribution of mass, creates new stresses, weakens the structure. A kilometer, wide snowball held together by nothing but its own weak gravity, and the frozen glue of dirty ice is not a robust object. As of August 2025, no outbursts had been detected. 3I, Atlos's brightness and activity level appeared steady, increasing gradually as expected. But that could change at any moment. Comets are notoriously unpredictable. They're fragile, dynamic, constantly evolving systems. We watch them with a mixture of fascination and caution, never quite sure what they'll do next. Here's the problem with observing 3I, at us around perihelion. From Earth, it will be on the opposite side of the Sun. It enters solar conjunction, meaning it will appear very close to the Sun in our sky, making it impossible to observe from ground-based telescopes. The comet's solar elongation, its angular separation from the Sun, will be less than 30 degrees from early October to early November. You can't point a telescope at something that close to the Sun without frying your equipment, or, if you're looking through an optical telescope, your eyes. So Earth-based observers will lose sight of 3I, ADS at the very moment it reaches its most active state. But we have orbiters. We have spacecraft around other planets. Mars orbiters, in particular, have a great view of 3I, ATIOS in early October, because the comet passes within 28 million kilometers of Mars on October 3rd. From Mars' perspective, 3I, ATIOS might reach magnitude 11, bright enough for the high-resolution cameras on Mars orbiting spacecraft to potentially image it. Whether those missions will divert resources to observe an interstellar comet, instead of focusing on their primary objectives of studying Mars, is another question. Science missions are tightly scheduled, every minute planned years in advance. Asking them to observe a comet means asking them not to do something else, but the opportunity is there. The Juno spacecraft orbiting Jupiter is another possibility. 3I ATIOS will pass about 54 million kilometers from Jupiter in March 2026, several months after perihelion. Juno has cameras, Juno has instruments, but Juno is also low on fuel and has engine issues. Redirecting it to observe a distant comet might not be feasible or wise. Still, people are talking about it. People are crunching the numbers, seeing if it's possible, seeing if the science return would be worth the risk and the resource expenditure. The Jupiter Icy Moons Explorer, JUIC, will pass within 64 million kilometers of 3I, ATIOS in early November 2025. JUIC is a European Space Agency mission currently traveling through the inner solar system on its way to Jupiter, where it will study the planet's icy moons Europa, Ganymede, and Callistos. The spacecraft has cameras, spectrometers, particle sensors. It could, in theory, observe 3I ATIOS, and apparently they're going to try. ESA announced that JUIC will attempt observations of the comet in November using several instruments. The data won't reach Earth until February 2026 because of the spacecraft's position and the challenging thermal conditions it's experiencing during its inner solar system transit. But the observations will happen. We'll get another view of 3I, ATIOS from a spacecraft perspective. From instruments designed to study icy moons, now turn toward an interstellar visitor that might carry clues about ice and organics from another stellar system entirely. After perihelion, after the solar conjunction ends, 3I, ATIOS will emerge back into view from Earth's perspective in November 2025. It will be moving away from the Sun, heading back toward the outer solar system and eventually interstellar space. As it recedes, it will fade. The solar heating will decrease. The outgassing will slow. The coma will shrink. The tail will weaken. By early 2026, 3I, ATIOS will probably be too faint for most ground-based telescopes to observe effectively. We'll need the biggest instruments, the most sensitive detectors, long exposure times to capture enough photons to learn anything useful. And eventually, even those won't be enough. The comet will fade below the detection threshold of everything we have, becoming just another invisible speck in the darkness, indistinguishable from the billions of distant galaxies and asteroids and stars that fill the sky. Our window to study 3I, ATIOS, is closing. It opened in July 2025 when ATOS found it. It will close sometime in early to mid-2026, when the comet becomes too faint to observe. That's maybe a year total. 12 months to answer questions about an object that has existed for billions of years and will continue existing for billions more. It's frustratingly brief, but it's what we have, and astronomers around the world are making the most of it, submitting telescope proposals, requesting observing time, coordinating campaigns to ensure continuous coverage across different wavelengths and different instruments. The scientific papers are pouring out already. Studies on the orbit, the composition, the activity rates, the physical properties. Each one adds a small piece to our understanding, but the puzzle is far from complete. We know 3I ATOS is water-rich, carbon dioxide-rich, carbon chain-poor, and nickel-emitting. We know it's ancient, probably billions of years old. We know it came from interstellar space on a trajectory that happened to align with our solar system's plane. We know it's outgassing more vigorously than it should at its distance from the Sun. We know its nucleus is probably less than a kilometer across, rotating every 16 hours or so, covered in some kind of surface material that affects how volatiles escape. But we don't know where it came from, not specifically. We can trace its trajectory backward through space, calculate where it was 1 million years ago, 10 million years ago, but uncertainties accumulate. Small errors in measuring its current velocity compound over time until the possible origin points spread across a huge volume of the galaxy. The September study that found 3I ATLAS past near 5 known stars in the past 10 million years is tantalizing. But none of those stars can definitively be identified as the comet's parent system. It might have come from one of them. It might have come from an unknown star we haven't catalogued. It might have been ejected from its birth system so long ago that the star has since moved to a completely different location in the galaxy, making any connection impossible to trace. This is the fundamental frustration of studying interstellar objects. They arrive with no return address, no identification, no clear history. They're cosmic mysteries wrapped in ice and dust, carrying chemical signatures we can measure but not fully interpret, because we don't know the context. We don't know what kind of star they came from, what kind of planetary system surrounded that star, what conditions existed in the protoplanetary disk when these comets formed. We can make educated guesses based on the composition we measure, but they're still guesses. The high carbon dioxide content of 3I ATOS suggests formation beyond the carbon dioxide frost line, probably several astronomical units from its parent star. The presence of carbon monoxide and carbonyl sulfide indicates even colder formation temperatures. The water content tells us the comet didn't form so far out that water itself couldn't condense. So we're talking about formation somewhere in the outer reaches of a protoplanetary disk, analogous perhaps to the Kuiper belt region of our own solar system, that zone beyond Neptune, where small icy bodies orbit in cold storage. Or maybe farther out, in the equivalent of our Oort cloud, that vast spherical shell of comets surrounding our solar system at distances of tens of thousands of astronomical units. The exact location depends on the parent star's properties, its mass, its luminosity, its composition, all things we can't measure because we don't know which star it is. The ancient age of 3I ATLAS adds another layer of complexity. If this comet is truly 7 to 14 billion years old, it formed when the Milky Way was younger, when the interstellar medium had different elemental abundances than it does today. Stars that formed early in galactic history incorporated less iron, less nickel, less of the heavy elements that are produced inside stars and scattered into space when those stars die. So maybe the nickel to iron ratio in 3I ATLAS isn't anomalous at all. Maybe it perfectly reflects the composition of the gas cloud that its parent star condensed from, a gas cloud that was relatively depleted in iron compared to more recent stellar formation regions. Maybe every comet from that era has similar properties, and we've just never seen one before. because interstellar visitors are rare, and this is only the third one we've detected. Or maybe the nickel-to-iron ratio was altered by billions of years of space weathering. Cosmic rays bombarding the surface, breaking chemical bonds, altering molecular structures. Solar wind from close stellar encounters ionizing surface materials. Radiation slowly changing the composition of the outer layers. We know that space weathering affects asteroids, darkening their surfaces, changing their spectral properties over time. Why wouldn't it affect comets too? The difference is that comets have volatiles that constantly resurface the nucleus. Every time 3I Atlas passes near a star, every time it heats up and outgasses, it sheds layers of material and exposes fresh ice underneath. That should mitigate space weathering effects. But if the comet spent billions of years in cold interstellar space, dormant and inactive, with nothing sublimating and no resurfacing happening, then maybe a weathered crust built up. Maybe what we're seeing now, as solar heating starts to strip away that crust, is a chemically altered surface layer that doesn't represent the comet's pristine interior composition. This is speculation piled on speculation, but it's the kind of speculation that drives science forward. You come up with hypotheses based on limited data, then you figure out what observations would test those hypotheses, then you go get those observations if you can. In the case of 3I Atlas, the key observations will come from watching how its composition and activity change as it approaches and passes perihelion. If the carbon dioxide to water ratio drops significantly when the comet gets closer to the sun and heats up more, that supports the idea of a volatile, depleted crust overlying a more water-rich interior. If the ratio stays constant, that suggests the comet is homogeneous, carbon dioxide, rich throughout. If we start seeing iron emission alongside the nickel in late October and November, that tells us something about depth, dependent composition or surface versus interior chemistry. If iron never shows up, that tells us something else. The James Webb Space Telescope observations in August 2025 provided our first detailed look at 3I Atlas's composition. But they were just a snapshot, a single set of measurements at one distance from the Sun. JWST is incredibly powerful, capable of detecting molecules that other telescopes miss, but it's also in high demand. Hundreds of research teams want to use it, and observing time is allocated months or years in advance through a competitive proposal process. Getting additional JWST observations of 3I Atlas means convincing the Telescope Allocation Committee that those observations are scientifically valuable enough to bump other approved programs. It means writing compelling proposals, demonstrating that the data you'll collect can't be obtained any other way, arguing that the fleeting nature of this interstellar visitor justifies the allocation of precious resources. Some research teams are doing exactly that. Proposals have been submitted for JWST observations of 3I Atlas in October and November 2025, timed to coincide with perihelion and the period immediately afterward, if approved and executed. Those observations will provide a second compositional snapshot at a different solar distance, allowing direct comparison and giving us insight into how the comet's outgassing changes with temperature. But there's no guarantee those proposals will be approved. JWST time is arguably the most valuable commodity in astronomy right now. Every hour of observing time has to be justified, prioritized, weighed against competing scientific objectives. Ground-based telescopes are easier to access, and they're working overtime on 3I Atlas, the Very Large Telescope in Chile, the Gemini telescopes in Hawaii and Chile, the Keck Observatory in Hawaii, numerous smaller facilities around the world. They're collecting spectroscopy, photometry, imaging, time series data. They're watching for outbursts, measuring brightness variations, tracking the development of the tail and coma. Every clear night is an opportunity to learn something new, and astronomers are taking advantage of it. The data is accumulating in archives, being analyzed by researchers, slowly building into a comprehensive picture of this interstellar visitor. But there are limitations to what ground-based telescopes can do. Earth's atmosphere absorbs many wavelengths of light, particularly in the ultraviolet and infrared, where many molecular signatures appear. Water vapor in the atmosphere blocks certain infrared bands where we'd love to detect cometary molecules. Atmospheric turbulence blurs images unless you're using adaptive optic systems, and even those have limits. You can only observe when the comet is above the horizon, when the sky is dark, when clouds aren't blocking the view. For 3I ATS, the solar conjunction from early October to early November means a forced observing gap at the most scientifically interesting time. That's just bad luck, bad timing, the vagaries of orbital mechanics that nobody can control. Space-based telescopes don't have those limitations, but they have others. Swift, Hubble, and JWST have all observed 3I ATS successfully, providing data that ground-based instruments can't match. But space telescopes are expensive to operate, have limited lifetimes, and serve many different scientific communities. Getting observing time requires proposals, peer review, scheduling coordination. And some space telescopes aren't designed for comet observations at all. They can do it, but it's not their primary mission, so convincing the mission teams to divert resources is challenging. There's another space asset that could potentially observe 3I ATLAS, though nobody's talking about it much in the scientific literature. The James Webb Space Telescope isn't the only major infrared observatory in space. There are military and intelligence satellites with infrared sensors designed to detect missile launches and track satellites. Those sensors are sensitive. They cover large areas of sky, and they're always operating. If any of those systems happen to catch 3I ATS in their field of view, the data would be classified, unavailable to civilian scientists, probably never acknowledged publicly. It's frustrating to think that useful scientific data about an interstellar visitor might exist, but remain locked away for national security reasons. But that's the reality of how space assets are distributed between civilian and military applications. Maybe decades from now, some of that data will be declassified, or maybe not. The amateur astronomy community has been surprisingly active in observing 3I ATLAS. You don't need a professional observatory to contribute useful data. Skilled amateur astronomers with backyard telescopes, good cameras, and knowledge of image processing techniques can measure the comet's position, brightness, and basic appearance. Those measurements help refine the orbital calculations, track activity variations, and provide continuous monitoring when professional telescopes aren't available. There's a long tradition of amateur contributions to comet science, dating back centuries to when there was no clear distinction between amateur and professional astronomers anyway. That tradition continues with 3I ATS, with observers around the world posting images and measurements to online forums and databases, building a collective understanding of the comet's behavior. Some of the most interesting amateur observations involve searching for subtle features in the coma and tail. Professional telescopes get limited observing time, usually just enough to collect the data needed for specific scientific objectives. Amateur observers can watch the comet for hours or even all night, taking hundreds of images, looking for transient phenomena that might not be captured in a brief professional observation. Outbursts, jets, disconnection events where the tail breaks off, spiral patterns in the coma caused by rotating jets from the nucleus. These features can appear and disappear on timescales of hours, and catching them requires patient monitoring. The amateur community provides that monitoring, serving as a distributed network of eyes, constantly watching the sky. The public reaction to 3I ATS has been muted compared to Oumuamua. When Oumuamua was discovered, it generated enormous public interest, partly because it was the first confirmed interstellar object, partly because its unusual properties sparked speculation about alien spacecraft. 3I ATLAS doesn't have that novelty factor. It's the third interstellar object, and while that's scientifically exciting, it doesn't capture the public imagination the same way. The fact that it's behaving like a comet, even an unusual one, makes it seem less exotic than Oumuamua's strange, dry, accelerating nature. And 3I Etilas is faint, requiring serious equipment to see. It's not going to be visible to the naked eye, not going to put on a spectacular show for casual sky watchers. Great comets like Hale, Bop, or Comet McNaught become cultural phenomena because anyone can walk outside and see them blazing in the sky. 3I Etilas will never be that comet. It's a scientific target, fascinating to researchers, but not a public spectacle. That said, the scientific community is deeply engaged with 3I Etilas, and that engagement is producing results. The rate of paper publication has been impressive. Within 2 months of discovery, multiple teams had published studies on the orbit, composition, activity, and physical properties. More papers are in preparation, going through peer review, waiting to be published. By the time 3I Etilas fades from view in early 2026, there will probably be dozens of scientific papers about it in the literature. That body of work will become the primary legacy of this interstellar visitor. The accumulated knowledge that outlasts the comet's brief passage through our observable sky. One area that's receiving particular attention is the question of how common interstellar objects like 3I Etilas actually are. Before Oumuamua, we had only theoretical predictions suggesting that interstellar objects should occasionally pass through the solar system. Those predictions were based on models of planetary system formation and evolution, which indicated that giant planets should eject large numbers of small bodies during their migration and gravitational interactions. Those ejected bodies would wander through interstellar space, and occasionally, some of them would pass through other star systems. The models predicted we should detect 1 or 2 interstellar objects per year with our current survey telescopes if we were looking carefully. Oumuamua was discovered by Pan-STARRS, a telescope system designed to find potentially hazardous asteroids. 2I Borisov was found by amateur astronomer Gennady Borisov using a telescope he built himself. 3I Etilas was discovered by the Etilas system, also designed primarily for asteroid detection. None of these were dedicated interstellar object surveys. They were all serendipitous discoveries. Objects that happened to pass through the detection zone of telescopes looking for something else. That suggests the actual population of interstellar objects passing through the solar system might be higher than we're currently detecting, simply because we're not optimized to find them. Several studies have used the discovery circumstances of Oumuamua, 2I Borisov, and 3I Etilas to estimate the total population of interstellar objects and the rate at which they pass through the solar system. The numbers vary depending on the assumptions, but a reasonable estimate is that there might be several interstellar objects, larger than 100 meters in diameter, passing within Earth's orbit every year. Most of them go undetected because they're too faint, too fast moving, or in the wrong part of the sky when our telescopes are looking elsewhere. As survey telescopes improve, as we build more sensitive instruments with wider fields of view, the detection rate should increase. The upcoming Vera Rubin Observatory, currently under construction in Chile, will be a game changer for interstellar object detection. Once operational, probably in 2025 or 2026, it will survey the entire visible sky every few nights, detecting faint objects that current telescopes miss. Simulations suggest Vera Rubin could detect dozens of interstellar objects per year, maybe more. That would transform the field from studying rare curiosities to analyzing a population, looking for patterns, categorizing different types, understanding the demographics of ejected objects from planetary systems across the galaxy. 3I Etilas is giving us a preview of what that future might look like. It's teaching us what to look for, what kinds of observations are most valuable, what questions are worth asking when the next interstellar comet arrives, and the one after that, and the one after that, will be better prepared. We'll know which instruments to use, which wavelengths to prioritize, which measurements to make first. We'll have a baseline for comparison, a context for interpretation. 3i, Atlas is building that baseline. The comet's trajectory through the solar system is taking it on a path that, coincidentally, brings it relatively close to several interesting locations. It passed within about 28 million kilometers of Mars in early October, as mentioned. That's roughly 75 times the Earth-Moon distance. Not particularly close by solar system standards, but close enough that Mars-based observers would see the comet as a reasonably bright object. Whether the various Mars orbiters actually observed it depends on whether mission planners decided the science return justified the deviation from normal operations. Those decisions happen behind closed doors, based on technical assessments and scientific priorities that aren't always publicized. We might not know if Mars orbiters captured images of 3i, ATRs until months after the fact, when data gets processed and researchers start publishing results. The geometry of 3i, Atlas's orbit, also brings it relatively close to the ecliptic plane during its passage through the inner solar system, which means it crosses the orbits of several planets. It crossed Mars' orbital path, it will cross Earth's orbital path, it crosses the orbits of Venus and Mercury on its way toward perihelion. This doesn't mean close encounters with those planets, just that the comet's trajectory intersects the imaginary lines traced by their orbits. The actual planets are millions of miles away, at different points in their own orbits. But these orbital crossings are interesting from a dynamical perspective, because they represent points where gravitational interactions could, in principle, slightly alter the comet's trajectory. In practice, the gravitational influence of planets on 3 Atlas is minimal, because the comet isn't passing close enough to any of them for significant perturbations. Its hyperbolic trajectory is locked in, determined primarily by its interstellar velocity and the Sun's gravity. Calculating that trajectory with precision has been an ongoing effort since discovery. Early orbital solutions, computed with just a few days of observations, had substantial uncertainties. The position of the comet was well constrained, but small uncertainties in its velocity translated into large uncertainties about where it would be months later. As more observations accumulated, the orbital solution improved, uncertainty shrank, predictions became more reliable. By August 2025, after 2 months of tracking, the orbit was enough determined that astronomers could confidently predict perihelion to within a few hours and a few thousand kilometers. That's important for planning observations, coordinating campaigns, ensuring that telescopes are pointed at the right place at the right time. But even with good orbital data, there's a complication. Comets don't follow purely gravitational trajectories. The outgassing of volatiles creates a rocket effect, non-gravitational forces that push the nucleus in directions that depend on which side is outgassing most strongly. For a rapidly rotating nucleus with symmetric outgassing, these forces might average out to zero. But for a nucleus with asymmetric activity, with jets preferentially pointing in certain directions, the rocket effect can significantly alter the trajectory over time. This is well documented for solar system comets. Comet Halley, for example, arrives at perihelion several days later than purely gravitational calculations predict, because outgassing has been slowing it down over multiple orbits. For 3ILS, the non-gravitational forces are harder to model, because we don't know the nucleus shape, rotation axis orientation, or jet distribution. Astronomers are watching the comet's position carefully, comparing observed positions to predicted positions based on gravitational calculations alone. Any discrepancy indicates non-gravitational forces at work. So far, through August 2025, no significant non-gravitational acceleration has been detected. But that could change as the comet becomes more active near perihelion. If 3i Atlas does show non-gravitational acceleration, measuring it precisely could tell us something about the outgassing distribution on the nucleus, which in turn tells us something about surface properties and activity patterns. This is exactly what happened with Oumuamua. That object showed clear non-gravitational acceleration, which led to enormous controversy. Some researchers argued the acceleration was consistent with cometary outgassing, even though no coma or tail was detected. Others said the acceleration was too large to be explained by outgassing without visible activity, suggesting alternative explanations like light pressure acting on a thin, reflective object. That alternative explanation, proposed by Harvard astronomer A.V. Loeb, suggested Oumuamua could be an artificial object, a light sail from an alien civilization. Most astronomers dismissed that idea as extremely speculative, lacking evidence, invoking exotic explanations before exhausting mundane ones. The debate got heated, personal, unpleasant. It's still not fully resolved, though the consensus view is that Oumuamua was probably a comet with very low outgassing rates or some unusual surface properties that prevented visible coma formation. 3I Attilas doesn't have that ambiguity. It's clearly a comet, clearly outgassing, clearly showing all the expected signs of cometary activity. If it shows non-gravitational acceleration, nobody's going to suggest alien spacecraft. It'll just be another data point for understanding comet outgassing. But it's interesting that the first interstellar object sparked exotic speculations, while the third one doesn't. Even though 3I ATLS has its own anomalous properties, maybe the astronomical community learned from the Oumuamua experience, became more cautious about jumping to extraordinary conclusions. Or maybe 3I ATLS just fits conventional categories well enough that there's no need to invoke anything beyond standard comet physics, however weird the details might be. The composition data from JWST has sparked comparisons to specific solar system comets that show similar characteristics. The high carbon dioxide abundance is reminiscent of Oort cloud comets. Those distant visitors that formed in the outer solar system billions of years ago and got ejected to vast distances by gravitational interactions with giant planets. Oort cloud comets spend most of their time in cold storage, far from the sun's heat, preserving primordial volatiles that would sublimate away in the inner solar system. When they occasionally fall back toward the sun, they carry chemical signatures from the early solar system, time capsules from an era we can't access any other way. 3I Attilas has similar composition to some Oort cloud comets, which suggests it might have formed in analogous conditions in the outer reaches of its parent planetary system. But there are differences too. The carbon, chain depletion, the nickel to iron ratio, the specific abundances of various molecules. These differences could reflect variations in the formation environment, differences between 3I Attilas's parent star system and our own. Or they could reflect the comet's ancient age, chemical evolution over billions of years. Disentangling formation environment from subsequent processing is one of the central challenges in interpreting composition data. One molecule that astronomers particularly want to detect in 3I ATLAS is molecular nitrogen, N2. This is the dominant molecule in Earth's atmosphere, a major component of Titan's atmosphere, and a volatile ice that should be present in comets if they formed in cold enough environments. But molecular nitrogen is notoriously difficult to detect in comets because it doesn't have strong spectral features in the wavelengths where we typically observe. It's symmetric, non-polar, doesn't emit or absorb light efficiently. The best way to detect it is indirectly, by looking for molecules that form when nitrogen is present. Cyanide is one such molecule. The CN we're seeing in 3I Atlas probably came from larger nitrogen-bearing organic compounds breaking down under UV radiation. But direct detection of molecular nitrogen would be valuable, because it would tell us about the temperature conditions in 3I ATLAS's formation region. Nitrogen only condenses into solid ice at extremely low temperatures below about 35 Kelvin. If 3I Atlas has significant nitrogen ice, it must have formed in one of the coldest regions of its parent protoplanetary disk, analogous to the outer reaches of our Kuiper belt or beyond. That would be consistent with the high abundances of other super volatile ices like carbon dioxide and carbon monoxide. It would paint a picture of a comet that formed very far from its parent star, in conditions similar to, or even colder than the conditions where Pluto and Triton formed in our solar system. Unfortunately, detecting molecular nitrogen in 3I ATIAS is probably beyond the capabilities of current instruments. It would require observations in specific ultraviolet wavelengths, where nitrogen has weak absorption features. And those observations would need to be done from space, with specialized instruments. The Hubble Space Telescope has the right wavelength coverage, but whether it has the sensitivity to detect weak nitrogen signals from a faint, distant comet is questionable. It might be attempted, proposals might be submitted, but success is far from guaranteed. Other molecules on the wish list include formaldehyde, methanol, ammonia, and various organic compounds. Some of these have been detected in solar system comets and would provide additional compositional constraints for 3I ATLAS. Methanol, for example, is often found in comets and is thought to form on icy grains in the protoplanetary disk before those grains get incorporated into comet nuclei. The methanol-to-water ratio varies between different comets and might correlate with formation location or temperature. Measuring it in 3I ATIAS would add another piece to the compositional puzzle. Ammonia is particularly interesting because it's a potential biosignature, a molecule associated with life processes. Of course, ammonia in a comet doesn't mean life. It just means nitrogen chemistry happened in the comet's formation environment or on its surface over time. But ammonia is also chemically interesting because it can combine with water ice to form hydrates, solid compounds that are more stable than pure ammonia ice. The presence or absence of ammonia and ammonia hydrates tells us something about the thermal and chemical history of the comet material. All of these molecules require different observing strategies, different wavelengths, different instruments. No single telescope can detect everything. That's why coordinated multi-instrument campaigns are so important for comets like 3I ATLAS. You use SWIFT for UV observations of hydroxyl and molecular oxygen. You use JWST for infrared spectroscopy of carbon dioxide, carbon monoxide, and organics. You use ground-based optical telescopes for cyanide, nickel, and other atoms and molecules with visible light signatures. You use radio telescopes for molecules like hydrogen cyanide and methanol that have strong rotational transitions in the radio spectrum. Each instrument contributes a piece, and you assemble them all into a complete compositional picture. Radio observations of 3I ATIAS have been attempted by several facilities, including ALMA, the Atacama Large Millimeter Array in Chile, one of the most powerful radio telescope arrays in the world. ALMA can detect molecules like carbon monoxide, hydrogen cyanide, methanol, and others that are difficult or impossible to see at other wavelengths. If approved and executed, ALMA observations would provide crucial data on the comet's volatile inventory, measuring production rates and abundances that complement the UV and infrared measurements from other telescopes. But ALMA, like all major facilities, is heavily oversubscribed. Observing time is allocated competitively, and comet observations compete with studies of star formation, galaxy evolution, protoplanetary disks, and dozens of other research areas. Getting ALMA time for 3I ATLAS means convincing the proposal reviewers that these observations are scientifically important and time-sensitive. The time-sensitive part is easy. Interstellar comets are rare, fleeting opportunities. Once 3I ATIAS leaves, we won't get another chance to study it. That urgency works in favor of comet proposals, but there's still no guarantee. The dust component of 3I ATLAS is another area of active investigation. Comets release both gas and dust, and the ratio between them varies depending on the comet's composition and the temperature at which volatiles sublimate. Some comets are dusty, releasing more dust than gas, creating thick comets that scatter lots of sunlight and make the comet appear bright. Other comets are gas-rich, releasing more volatiles than dust, creating thinner comets dominated by fluorescing molecules rather than scattered light. 3I ATIAS appears to be somewhere in the middle, neither extremely dusty nor extremely gas-rich. The dust-to-gas ratio measured in July and August was roughly consistent with typical comet values, around 1 to 2 by mass. That means for every kilogram of gas released, the comet is also releasing 1 to 2 kilograms of dust. The dust grains themselves range in size from submicron particles, smaller than the wavelength of visible light, up to millimeter-sized or larger chunks. Different sizes behave differently in the sunlight and solar wind. Small grains are pushed away from the comet more efficiently, forming diffuse tails. Large grains move more slowly, staying closer to the nucleus. Analyzing the dust involves both imaging and spectroscopy. Images show the spatial distribution of dust in the coma and tail, revealing structures like jets and streamers that trace the outgassing pattern from the nucleus. Spectroscopy reveals the dust composition, or at least gives hints about it. Dust grains reflect and scatter sunlight, and the wavelength, dependence of that scattering, tells you something about the grain size distribution and potentially the mineral composition. Silicate grains have different spectral signatures than carbonaceous grains, for example. The reddish color of 3I, Attias's coma suggests the dust contains organic compounds, probably tholins as mentioned earlier. Tholins form when simple hydrocarbons and nitrogen-bearing molecules are exposed to UV radiation and high-energy particles. The result is a complex mixture of organic polymers that appear reddish-brown. We see tholins on many outer solar system objects, including Pluto, Titan, and various Kuiper belt objects. The presence of tholins in 3I, Attias suggests its surface has been processed by radiation over its billions of years in interstellar space, creating this organic coating that now contributes to the dust released during outgassing. But there's likely also silicate dust in 3I, ATS. Minerals like olivine and pyroxene that are common in comets and asteroids throughout the solar system. These minerals form during the planet-building process, condensing out of hot gas in the inner regions of protoplanetary disks, and then getting mixed outward through turbulent processes and incorporated into comets forming in the outer disk. Every comet we've studied in detail contains silicate dust, and there's no reason to think 3I, Attilas would be different, just because it came from another star system. The basic physics and chemistry of planet formation should be universal, operating the same way everywhere in the galaxy. Detailed dust composition analysis would require a close-up mission, either a flyby or a sample return. Neither is going to happen for 3I ATLAS. The comet was discovered too recently for any spacecraft to be launched and reach it before it leaves the solar system. Spacecraft take years to plan, build, and launch, and 3I ATLAS is going to be long gone before any mission could reach it. This is the same problem we had with Oumuamua and 2I Borisov. By the time we discover these interstellar visitors, it's too late to mount a dedicated mission to study them up close. But that doesn't mean missions are impossible. It just means we need to be prepared in advance, with spacecraft ready to launch on short notice when an interstellar object is discovered. This idea has been proposed multiple times. Build a spacecraft, or even multiple spacecraft, designed for rapid launch and high delta-V capability to chase down interstellar objects. Keep them in storage, ready to go. Launch them within weeks of discovery. It's technically feasible with current technology. The main barriers are cost and political will. Convincing space agencies to build and maintain standby spacecraft for hypothetical targets that might not appear is a tough sell. One proposal calls for a spacecraft using solar sail propulsion, where a large, reflective sail is pushed by sunlight pressure to achieve high speeds without needing propellant. Solar sails have been successfully tested on small scale, and a dedicated interstellar object interceptor using this technology could potentially reach speeds of tens of kilometers per second, fast enough to catch up with objects like 3I ATLAS if launched soon after discovery. But again, this requires upfront investment, and space agency budgets are constrained, prioritized toward missions with guaranteed targets and clearly defined scientific objectives. Another approach is to task existing deep space missions with opportunistic observations of interstellar objects if trajectories happen to align. This is what's being attempted with JUICE and potentially with other missions in the right locations at the right times. It's not as good as a dedicated flyby, but it's better than nothing, and it leverages assets already in space rather than requiring new launches. The challenge is that most deep space missions have tight fuel budgets and can't afford large trajectory changes. They're already committed to their primary objectives, and deviating to observe an interstellar comet has to be carefully evaluated against mission constraints and scientific priorities. For 3I, ETIAS specifically, no close-up mission is possible, so we're limited to remote observations from Earth and Earth-orbiting spacecraft, with the possible exception of distant observations from a few spacecraft in favorable positions. That's frustrating, because remote observations can only tell us so much. We can measure composition, but only of the gases and dust being released. We can't sample the nucleus directly, can't measure its density or internal structure, can't see what's beneath the surface. We can estimate the nucleus size from brightness and assumptions about reflectivity, but we can't image it directly to see its shape and surface features. We're learning a lot, but we're also aware of how much we're missing, how much more we could learn with a close-up encounter. One of the surprising aspects of 3I, ETIAS's discovery, is how little advance warning we had. The comet was first detected at 4.5 AU from the Sun, already active, already visible. But looking back at archival data, astronomers found that TSS had imaged it months earlier at 6.4 AU. Why didn't anyone notice it then? Because TSS is an exoplanet mission, not a comet survey. The spacecraft is designed to monitor stars, looking for tiny dips in brightness caused by planets passing in front of them. The software pipelines are optimized for that specific task, not for detecting moving objects in the foreground. 3I, ALAS was in the TSS images, but nobody was looking for it, and the automatic detection systems weren't configured to find comets. This highlights a broader issue in astronomy. We collect vast amounts of data, far more than human astronomers can possibly examine by eye. Automated systems sift through the data, looking for specific phenomena of interest, and everything else gets ignored or archived without analysis. Valuable discoveries are probably hiding in archival data from numerous surveys, waiting for someone to look at them from a different perspective, waiting for algorithms designed to find different things. The detection of 3I, ETIAS in TESS archival data only happened after the comet was discovered by ATLAS and astronomers knew what to look for. Retrospective analysis is valuable for refining orbital calculations and understanding the comet's early activity, but it doesn't help with early warning or preparation for observations. This is spurring development of better automated detection systems. Machine learning algorithms trained to recognize comets, asteroids, and other transient phenomena in survey data, regardless of the primary mission objectives. If we can get better at finding these objects early, when they're still far from the Sun, we have more time to plan observations, request telescope time, coordinate campaigns. For interstellar objects in particular, early detection could make the difference between comprehensive study and missed opportunity. The ATLAS system that found 3I, ATLAS, is actually quite good at this. It's specifically designed to scan large areas of sky repeatedly, looking for anything that moves or changes brightness. It was built to find potentially hazardous asteroids, objects whose orbits might bring them close to Earth, but it also discovers comets as a byproduct. The system uses relatively small telescopes, just half-meter mirrors, but it covers enormous sky areas and operates automatically, taking images every night when weather permits, comparing new images to reference images to find anything different. When something moves between images, the software flags it, and human astronomers review the candidates to determine what's real and what's instrumental artifacts or image processing errors. ATLAS has been remarkably successful since it became operational. It's discovered hundreds of near, Earth asteroids, and dozens of comets. 3I. Atlas is perhaps its most scientifically significant discovery to date, the first interstellar object found by the system. The name 3I, Atlas, directly references this, marking it as the third interstellar object and crediting Atlas as the discovery survey. It's a naming convention that will probably continue as more interstellar objects are found. 4I, 5I, 6I, each with a designation indicating which survey or observer found it first. How many more will there be? When will the next interstellar visitor arrive? These questions are impossible to answer precisely because we don't know the true population of interstellar objects or the details of their spatial and velocity distributions in the galaxy. Statistical estimates suggest the next detectable interstellar comet could arrive within months or could be years away. It depends on the random trajectories of billions of ejected objects wandering through the Milky Way, on which ones happen to pass through our detection zone, on whether our telescopes are looking in the right direction at the right time. What we can say is that detection rates will improve. More survey telescopes are coming online. Existing surveys are being upgraded with more sensitive cameras. The Vera Rubin Observatory, once operational, will dramatically increase the discovery rate, not just for interstellar objects, but for everything that moves or changes in the sky. Within a decade, we might be detecting interstellar visitors regularly, maybe monthly or even more frequently. The field will transform from studying individual curiosities to analyzing populations, looking for patterns in composition and dynamics that tell us about planet formation processes throughout the galaxy. 3I, Atlas is preparing us for that future. Every observation technique developed for it, every analysis method refined, every scientific question asked becomes part of the toolkit we'll use on future interstellar visitors. The papers being published now on 3I, Atlas aren't just about this specific comet. They're establishing methodologies, setting baselines, creating frameworks that will apply to interstellar objects generally. Future researchers will cite 3I, Atlas papers when they discover the fourth and fifth and sixth interstellar comets, comparing compositions, looking for similarities and differences, building toward a comprehensive understanding of how comets form in diverse stellar environments. One particular question that 3I Atlas might help answer is whether interstellar objects show systematic compositional differences from solar system objects beyond just individual quirks. Do comets from other star systems have, on average, different volatile abundances than our comets? Are certain molecules more common or less common? Is there a characteristic interstellar comet composition that distinguishes them from locally formed comets? With only 3 data points, we can't answer these questions definitively. Oumuamua was compositionally mysterious because we barely observed it. 2I, Borisov looked fairly normal. 3I, Atlas's carbon dioxide, rich and carbon, chain depleted. That's not enough for statistical analysis, not enough to establish trends. But it's a start. Each new interstellar object adds to the dataset, and eventually, we'll have enough to do meaningful comparative studies. The chemical composition of comets isn't just scientifically interesting in abstract terms. It has real implications for understanding the origins of life. Comets contain organic molecules, the carbon-based compounds that serve as building blocks for biology. They contain water, ammonia, methanol, formaldehyde, hydrogen cyanide, and numerous other molecules that, while not alive themselves, are the raw materials from which life could potentially emerge. There's a long-standing hypothesis that comets delivered these molecules to early Earth, seeding our planet with the chemicals necessary for life to begin. Impacts from comets during Earth's first billion years would have added volatiles to the atmosphere and oceans, contributed organic material that could participate in prebiotic chemistry. If that hypothesis is correct, then studying comet composition tells us something about the ingredients that were available when life began on Earth. And studying interstellar comets tells us whether those same ingredients are available elsewhere in the galaxy. If 3I Telos has similar organic chemistry to our comets that suggests comet composition is fairly universal, determined by basic chemical processes that operate the same way in all protoplanetary disks. That would strengthen the argument that the raw materials for life are common throughout the galaxy, not unique to our solar system. Conversely, if interstellar comets turn out to have very different chemistry, that might indicate that the specific mix of molecules that enabled life on Earth is rarer, more dependent on local conditions in our particular protoplanetary disk. 3I, Telos contains organic molecules. We know that from the cyanide detection and the reddish color of its dust. The specific inventory of organics, the complexity of the molecules present, whether there are amino acids or nucleobases or other biologically relevant compounds, those are questions that would require more detailed analysis than we can perform with remote observations. Sample return would be ideal. Bringing actual comet material back to Earth for analysis in laboratory instruments that can detect trace compounds and determine molecular structures with precision impossible from telescopes. But as discussed, sample return from 3I ATRs isn't feasible. Still, the fact that we're detecting complex organic chemistry in an object from another star system, an object that formed billions of years ago in a different protoplanetary disk around a different star, is profound. It suggests that organic chemistry is not just a local phenomenon, but a universal feature of planet formation. Wherever stars form, wherever protoplanetary disks exist, carbon chemistry happens, complex molecules form, comets accumulate those molecules and carry them through space. This universality has implications for astrobiology, for the search for life beyond Earth. If the chemical ingredients for life are common throughout the galaxy, then life itself might be common, emerging wherever conditions are favorable. Wherever planets have liquid water and energy sources and sufficient time for chemistry to explore the possibilities. Of course, going from chemistry to biology is an enormous step, one we don't fully understand even in the context of Earth's origins. The transition from non-living molecules to self-replicating, evolving, metabolizing systems is one of the great unsolved problems in science. Comets can deliver molecules, but molecules alone aren't life. Something has to organize them, concentrate them, allow them to interact in ways that lead to complexity and self-replication. On Earth, that probably happened in some specific environment, maybe tidal pools, maybe hydrothermal vents, maybe beneath ice, maybe in warm ponds. We don't know. But the starting materials, the molecular toolkit, quite possibly came from space, delivered by comets and asteroids. 3I, Telos is a reminder that space is full of chemistry, that molecules are everywhere, that the building blocks of life are being created and destroyed, and transported across vast distances, constantly. The comet we're observing now was built from molecules that formed in a protoplanetary disk billions of years ago. Molecules that survived the comet's ejection from its parent system, survived billions of years drifting through interstellar space, exposed to cosmic rays and vacuum, and are now being released in our solar system where we can detect and analyze them. It's an incredible journey, and we're witnessing just the final act. As October 2025 approaches, the scientific community is preparing for perihelion observations, working around the limitations imposed by solar conjunction. The observing strategies being developed involve coordinating ground-based telescopes in both hemispheres to maximize coverage before and after the conjunction period, using space-based assets that can observe closer to the Sun than ground-based telescopes can, and potentially leveraging Mars-orbiting spacecraft if mission teams decide the science return justifies the operational complexity. The expected increase in activity near perihelion will provide crucial data. Water production rates should increase as the comet heats up, possibly dramatically if there's fresh ice beneath the surface that becomes exposed. The carbon dioxide to water ratio might change if carbon dioxide preferentially sublimits from the outer layers while water dominates at higher temperatures. New molecular species might become detectable as different ices reach their sublimation temperatures. The dust production rate will likely increase, making the coma larger and the tail longer. All of these changes are observables that constrain physical models of the nucleus and its composition. There's also the possibility, mentioned earlier, of outbursts or fragmentation. Comets are fragile. They're not solid rock, but rather loosely consolidated mixtures of ice and dust held together by weak gravity and ice cohesion. Thermal stresses from solar heating can crack the nucleus, create new areas of active outgassing, or even split the nucleus into multiple pieces. When comet Shoemaker-Levy 9 passed close to Jupiter in 1992, tidal forces tore it apart into more than 20 fragments that later impacted the planet in a spectacular series of collisions observed by telescopes worldwide. 3I, Attilas won't experience tidal forces that strong because it's not passing close to any massive planet, but thermal stresses alone can fracture a small, fragile nucleus. If 3I Attilas fragments, it would be both scientifically valuable and visually dramatic. Fragmentation exposes fresh interior material, allowing us to see compositional differences between the surface and the interior. It also creates multiple nucleus fragments with different surface areas and temperatures, potentially showing different activity patterns. And it provides natural experiments in comet physics, allowing us to observe how outgassing affects small chunks of material with different sizes and rotation states. 2I, Borisov showed evidence of fragmentation, or at least significant disruption, during its solar system passage. And the observations of that event contributed substantially to understanding its physical properties. Whether 3I Attilas will fragment is impossible to predict. It depends on the internal structure, the strength of the material, the distribution of volatile ices, the thermal stresses induced by solar heating, and probably some random factors like the specific locations of cracks or weak points in the nucleus. All we can do is watch carefully, monitor the brightness and activity level, look for sudden changes that might indicate something dramatic happening. Amateur astronomers, with their ability to provide continuous monitoring, could play a crucial role in detecting outbursts or fragmentation events if they occur. The post-perihelion phase, starting in November 2025 when 3I Attilas emerges from solar conjunction, will be critical for testing models developed from the pre-perihelion data. If models predict certain activity levels or compositional ratios based on pre-perihelion observations, and those predictions are confirmed by post-perihelion measurements, that validates the models and increases confidence in our understanding of the comet. If predictions fail, if the comet behaves differently than expected, that tells us something important was missing from our models. Some physical process or compositional property we didn't account for. Either outcome advances science. But predictions that fail are often more interesting because they point toward new physics or chemistry we didn't know about. One specific prediction that will be tested concerns the carbon dioxide to water ratio. If 3I Attilas has a volatile, depleted crust as some models suggest, then near perihelion when temperatures are highest, that crust might be partially removed by sublimation and erosion, exposing more water-rich material beneath. In that case, the carbon dioxide to water ratio should decrease as perihelion approaches and water becomes more dominant. Alternatively, if the high carbon dioxide abundance is intrinsic to the comet throughout its interior, the ratio should stay roughly constant or increase slightly as carbon dioxide continues to sublimate more easily than water. Measuring this ratio at multiple points before, during, and after perihelion will distinguish between these scenarios. Similarly, if ion emission appears alongside nickel in late October or November, that would suggest the surface is being removed and fresh material with different metal content is being exposed. If ion never appears, that strengthens the case that the nickel, without ion signature, is fundamental to this comet's composition, not just a surface phenomenon. These are testable predictions with clear observational signatures, exactly the kind of science that moves the field forward. The international coordination required for 3I ATIOS observations is impressive. Telescopes in Chile, Hawaii, Spain, Australia, South Africa, and numerous other locations are contributing data. Research teams from the United States, Europe, Japan, Australia, and other countries are collaborating, sharing data, co-authoring papers. This kind of global scientific cooperation is one of the great successes of modern astronomy. Despite political tensions and economic disparities between nations, the astronomical community functions as a truly international enterprise, with scientists from different countries working together toward common goals. That cooperation is essential for studying objects like 3I ATIOS, because optimal observations require facilities distributed around the Earth. When it's daytime in Chile, and the telescopes there can't observe, it might be night in Australia, where observations are possible. When 3I ATIOS sets below the horizon from one observatory, it might be rising at another. Coordinating observations across longitudes ensures continuous coverage, minimizing gaps in the data that could cause us to miss transient events. This is particularly important for detecting outbursts or measuring rotation periods, both of which require monitoring the comet over timescales of hours to days. The data sharing arrangements vary depending on the observatories and instruments involved. Some facilities require proprietary periods, where the observing team has exclusive access to the data, usually for a year or so, to allow them to publish their results before making the data public. Other facilities make data publicly available immediately or after short delays. For 3I ATIOS, the scientific value of immediate data sharing is high, because the observing window is limited and coordination between teams is beneficial. Many research groups are sharing data informally, sending measurements and spectra to colleagues who need them for their own analyses, accelerating the pace of discovery beyond what would happen if everyone worked in isolation. This rapid data sharing is facilitated by modern communication technologies. Researchers can email large data files, use cloud storage services, participate in video conferences to discuss results in real time. The 3I ATIOS research community is effectively operating as a distributed international collaboration, even though there's no formal organizational structure. It's emergent cooperation driven by shared scientific interests and the recognition that everyone benefits when data and ideas flow freely. The publication process is also adapting to the rapid pace of discoveries. Traditionally, scientific papers go through peer review that can take months. Reviewers evaluate the methodology, check the calculations, assess whether the conclusions are justified by the data. It's a careful, conservative process designed to ensure that published results are reliable. But for fast, moving fields like interstellar object research, waiting months for peer review means the results might be outdated by the time they're published. 3I ATIOS will have faded from view before traditional publication timelines would allow papers to appear in journals. To address this, many researchers are posting preliminary results to Archive, an online preprint server, where papers appear immediately without peer review. These preprints allow the scientific community to see and build on new results quickly, while the papers simultaneously go through formal peer review for eventual journal publication. It's a compromise between speed and rigor, allowing rapid communication while maintaining eventual quality control. Most of the 3I ATIOS papers published so far appeared first on Archive, sometimes just days after the observations were made, with formal journal publication following weeks or months later. This system works reasonably well for communicating within the scientific community, but it creates challenges for public communication and science journalism. Journalists covering space science have to decide whether to report on preprint results that haven't been peer-reviewed or wait for formal publication, by which time the story might no longer be timely. Different outlets make different choices, leading to varying levels of caution and accuracy in public reporting about discoveries like 3I ATIOS. Some reports are excellent, carefully explaining the science and the uncertainties. others are sensationalized, emphasizing speculative aspects or misrepresenting preliminary findings as definitive conclusions. The speculation about artificial origins for 3I, ATOS, mentioned earlier in the context of its unusual trajectory, is an example of how preliminary observations can spawn exaggerated claims. The paper suggesting 3I, ATOS might be an extra terrestrial spacecraft was published quickly, before comprehensive compositional data was available, based primarily on the orbital characteristics and early activity measurements. It got significant media attention because alien spacecraft is a compelling headline, but subsequent observations showing clear cometary composition and behavior have largely debunked that idea, at least within the scientific community. 3I, ATOS is a comet, albeit an unusual one, not a probe from another civilization. This pattern repeats with interstellar objects because they're rare and mysterious enough that extraordinary explanations seem worth considering, at least briefly. Oumuamua went through the same cycle. Initial observations showing unusual properties led to speculation about artificial origins, which generated media coverage and public interest, followed by more mundane explanations as additional data accumulated. The scientific process is self-correcting, with speculative ideas being tested and usually rejected as evidence accumulates. But the public often sees only the initial speculation and not the subsequent correction. For 3I, ATOS, the compositional data from JWST and the Very Large Telescope pretty definitively establishes it as a natural object, a comet with composition and behavior consistent with formation in a protoplanetary disk around another star. The unusual characteristics: the high carbon dioxide abundance, the carbon chain depletion, the nickel emission without iron. These are puzzles that require explanation. But they're within the range of natural variability we might expect from comets formed in different environments. They don't require exotic hypotheses about artificial objects or intelligent intervention. That said, the unusual trajectory alignment with the ecliptic plane remains somewhat mysterious. The probability of an interstellar object arriving with such a low inclination relative to our solar system's plane is not zero, but it's small. If we detect dozens of interstellar objects, and many of them have low inclinations, that would suggest something about the velocity distribution of interstellar objects in the galaxy, maybe indicating they're preferentially ejected into the galactic plane, where most stars orbit. But with only 3 objects detected, we can't draw statistical conclusions. 3I, ATOS might just be a statistical fluke, an improbable trajectory that happened to occur, because the universe is large and improbable things happen occasionally. As October 2025 progresses toward perihelion, the observing cadence is intensifying. Telescopes that observed 3I, ATOS once or twice in July and August are now observing more frequently, sometimes every few nights when weather permits. The increased activity level makes the comet scientifically richer, with more detectable molecules and stronger emission lines that are easier to measure. Spectroscopy that required hours of exposure time in July might need only minutes in October. The dust tail is becoming more prominent, easier to image and analyze. In many ways, this is the peak observing period, the time when we can extract the maximum scientific value from 3I, ATOS, before solar conjunction and geometry conspire to make observations difficult. The brightness of 3I, ATOS, has been steadily increasing as it approaches the Sun, though not as dramatically as some comets that show explosive brightness increases near perihelion. The magnitude progression has been fairly linear in logarithmic scale, suggesting steady, predictable sublimation driven primarily by solar heating without major outbursts or unusual activity. As of late September 2025, the comet was around magnitude 12, requiring moderate-sized telescopes to observe, but within reach of serious amateur equipment. At perihelion in late October, if the brightness trend continues, it might reach magnitude 11 or possibly even magnitude 10, making it observable with smaller telescopes and enabling more observers to contribute data. But again, Comet brightness predictions are notoriously unreliable. Comets can suddenly brighten if they experience outbursts, or suddenly fade if they fragment, or if the active areas on the nucleus rotate away from sunward facing positions. The predicted brightness is based on extrapolating current trends, assuming nothing dramatic changes. Reality may differ from predictions, and if it does, that itself will be scientifically interesting, because it tells us something about the comet's physical behavior. One aspect of 3I, ATLAS that hasn't received as much attention as composition, but is equally important, is its thermal behavior. How efficiently does the nucleus absorb solar radiation? How much of that absorbed energy goes into heating the surface versus sublimating ice? What's the thermal conductivity of the nucleus material? Determining how heat flows from the surface into the interior. These thermal properties affect outgassing rates, activity patterns, and the comet's response to solar heating. Measuring thermal properties requires infrared observations at multiple wavelengths to determine the nucleus temperature. The Spitzer Space Telescope would have been ideal for this, but it was decommissioned in 2020. JWST can do thermal infrared observations and has observed 3I ATLAS. But whether those observations included thermal mapping at the appropriate wavelengths depends on the specific instrument modes used. Ground-based infrared telescopes, like those on Mauna Kea, can contribute, though atmospheric water vapor absorption limits their sensitivity in some infrared bands. The temperature of 3I ATLAS's nucleus depends on its distance from the Sun, its reflectivity, and its thermal inertia. At 3.5 AU, where Swift observed strong water outgassing, the equilibrium temperature for a dark, low thermal inertia surface would be around 160 to 180 Kelvin. That's cold by terrestrial standards, well below the freezing point of water, but it's warm enough for water ice to sublimate at appreciable rates, especially if the ice is porous or contains trapped volatiles that enhance sublimation. At perihelion, 1.36 AU, the temperature would rise to roughly 230 to 250 Kelvin for the same surface properties. That's still well below room temperature, but warm enough for vigorous outgassing if water ice is present. However, these temperatures are equilibrium values assuming the surface is in steady state with solar heating. Real comet nuclei are more complicated. They rotate, so different parts of the surface experience different amounts of sunlight over a rotation cycle. They have topography, with hills and craters creating shadows and varying solar incidence angles. They may have non-uniform composition, with some areas ice-rich and others dust-rich. And they have thermal lag, where the warmest surface temperatures occur not at local noon, but some time afterward. After heat has conducted into the subsurface and established a temperature gradient. All of these complexities affect the outgassing pattern, creating the jets and plumes we observe in the coma. 3I ATLAS shows evidence of asymmetric outgassing from the sunward, elongated coma morphology. That asymmetry could be due to rotation carrying active areas into and out of sunlight, or due to compositional heterogeneity, where some regions are more volatile, rich than others, or due to topographic effects, where certain surface features preferentially release gas. Distinguishing between these possibilities requires detailed modeling, combined with observations of how the coma structure changes over time as the nucleus rotates and as solar distance varies. The fact that 3I ATLAS was already active at 6.4 AU, as shown by the TESS observations, indicates either super-volatile ices like carbon monoxide or nitrogen, or some non-thermal energy source driving outgassing. Super-volatiles are the likely explanation, and the JWST detection of high carbon dioxide abundances supports this. Carbon dioxide sublimates readily at the temperatures present at 6 AU, and if the nucleus has substantial carbon dioxide ice, that could drive activity even at large solar distances. The released carbon dioxide gas could also entrain water ice grains, carrying them off the nucleus where they subsequently sublimate, creating the water-rich coma observed by Swift at smaller distances. This model of carbon dioxide-driven activity has been proposed for several solar system comets, including Comet Hale, BOP, which was famously active at enormous solar distances. Hale, BOP, was releasing carbon monoxide gas when it was beyond Jupiter's orbit, demonstrating that volatiles can drive substantial activity far from the Sun. 3I Attilas may be similar, with a composition enriched in carbon dioxide and possibly carbon monoxide relative to water, allowing it to be active farther from the Sun than typical water-dominated comets. Testing this model requires measuring production rates of different molecules at different solar distances and comparing them. If carbon dioxide production rate stays roughly constant, while water production increases as the comet approaches the Sun, that supports the model. If all volatiles increase together at similar rates, that suggests a different mechanism. The observations before and after perihelion will provide this data, allowing researchers to construct detailed thermal and outgassing models specific to 3I Attilas. These models aren't just academically interesting. They have practical implications for understanding how comets deliver volatiles to planets. If 3I Attilas type composition is common among interstellar comets, and if interstellar comets occasionally collide with planets in other star systems at rates similar to what occurs in our solar system, then the volatile delivery to those planets would reflect that composition. A carbon dioxide-rich comet population would deliver different chemistry to a planet than a water-dominated population. The balance between water, carbon dioxide, and other volatiles affects planetary atmospheres, oceans, and the availability of molecules for prebiotic chemistry. In our solar system's history, Earth was likely impacted by thousands or millions of comets during the first billion years. Those impacts contributed water and organics that became part of Earth's oceans and early atmosphere. If some of those impacts were from interstellar comets that happened to pass through our solar system billions of years ago, they might have delivered unusual chemistry compared to our native comets. There's no way to know this with certainty because the impactors are long since vaporized or buried. But it's an intriguing possibility that interstellar contributions to Earth's volatile inventory might have influenced the planet's early chemical evolution. 3I Attilas gives us a window into that process happening elsewhere. This comet will eventually leave our solar system and continue wandering through interstellar space. In 100,000 years, a million years, a billion years, it might pass through another star system. If that system has planets 3I Attilas could potentially impact one of them, delivering its cargo of water, carbon dioxide, organics, and metals to that planet's surface. The nickel cyanide, carbon dioxide, and other molecules we're detecting now might someday become part of another world's chemistry. It's a humbling thought that this ancient comet we're observing for a few months might interact with future worlds we'll never see, influenced by civilizations that might someday exist around stars we can barely resolve with our best telescopes. This perspective, thinking about 3I Attilas across billion-year timescales, across multiple stellar encounters, across the vast stage of galactic evolution, puts our observations in context. We're catching a brief snapshot of one moment in an unimaginably long journey. The comet was ancient before it arrived here and will remain ancient after it leaves. Our contribution is documenting this particular passage, adding one data point to its history, learning what we can in the limited time available. It's both frustrating and exciting, a reminder of how small our observational window is compared to cosmic timescales, but also how valuable each observation becomes when you realize it's documenting something unique and unrepeatable. Looking ahead to November and December 2025, after perihelion and after solar conjunction ends, the observing focus will shift to monitoring the comet's decline in activity as it moves back toward the outer solar system. The fade should be roughly symmetric with the brightening, following similar trends, but in reverse as solar distance increases and temperatures drop. By January or February 2026, 3I Attilas will probably be below magnitude 13, requiring large telescope for continued observations. By mid-2026, it may fade below magnitude 15, accessible only to the largest ground-based telescopes and space-based instruments. The exact fade rate depends on whether the nucleus remains intact or fragments, whether outgassing continues at large distances or shuts off quickly, and whether any surprise outbursts occur post-perihelion. Some comets show increased activity after perihelion rather than before, possibly because solar heating has penetrated deeper into the nucleus and created subsurface pressure that drives delayed outgassing. If 3I Attilas does this, it would extend the useful observing window and provide additional data for understanding its composition and structure. Eventually, though, 3I Attilas will fade beyond detection limits and disappear back into the darkness of interstellar space. Its trajectory will carry it out of the solar system at 58 kilometers per second relative to the Sun, heading toward a region of sky in the constellation Cetus. In 100,000 years, it will be hundreds of billions of kilometers away, farther than the Oort cloud, back in the realm between stars where it spent most of its existence. In a few million years, it might pass near other stars, experiencing brief moments of heating and activity similar to what we're witnessing now, then returning to dormancy for another long period of interstellar drift. The final catalogue of observations, the complete dataset from all telescopes and all observers, will be compiled into databases and archives, where future researchers can access it. This dataset will become the permanent scientific legacy of 3I Atlas, used by students and scientists decades or even centuries from now to study interstellar comets and compare them to newly discovered objects. Long after the comet itself has faded from view, the data will remain, constantly reanalyzed, reinterpreted in light of new theories and new understanding. This is how science progresses with rare phenomena. You can't experiment on interstellar comets, can't control variables, can't repeat observations under different conditions. You get one chance, one apparition, one dataset. That dataset has to serve all future research needs. Answer questions we haven't thought to ask yet, support analysis using techniques not yet invented. The comprehensiveness and quality of the observations matter enormously because we can't go back for more data. What we collect now is all we'll ever have for 3I Atlas. That responsibility weighs on the researchers planning observations. Every decision about which instrument to use, which wavelength to prioritize, which measurements to make, affects what science is possible years from now. There's no perfect observing strategy that addresses every question, only trade-offs and compromises guided by scientific judgment and practical constraints. The researchers involved are doing their best to maximize the scientific return, to collect data that will remain valuable and informative for as long as people study comets. And people will study comets for a very long time. Comets are windows into planet formation, into the composition of protoplanetary disks, into the processes that convert gas and dust into solid bodies. They're also potential delivery vehicles for water and organics to planets, possibly including the water and organics that made Earth habitable and enabled life to begin. Understanding comets means understanding our own origins, the cosmic processes that created the solar system and everything in it, including us. Interstellar comets add another dimension to that understanding, showing us that the processes we study locally operate throughout the galaxy, that comet formation is universal, that the building blocks of worlds are being created and distributed everywhere stars form. 3I Atlas is currently teaching us that lesson in real time. Every spectrum, every image, every measurement adds to our knowledge of how comets work, what they're made of, how they respond to sunlight, how they evolve over billions of years. The unusual characteristics that make 3I Atlas scientifically interesting are also teaching us about the diversity of comet properties, showing us that our solar system's comets don't represent the full range of what's possible. The high carbon dioxide, the carbon chain depletion, the nickel without iron. These aren't errors or anomalies, but genuine differences, reflecting formation in a different environment under potentially different conditions. Understanding those differences means understanding which aspects of comet properties are universal, determined by fundamental physics and chemistry that operates the same way everywhere, and which aspects are contingent, dependent on local conditions that vary between star systems. That distinction is crucial for extrapolating from what we know about our solar system to predictions about other planetary systems. If comet composition is highly variable, then predictions about volatile delivery to exoplanets must account for that variability. If comet composition is fairly uniform, then what we learn about our comets applies more directly elsewhere. 3i ATLAS suggests variability exists. The composition differs from typical solar system comets in specific ways, but it's not wildly different, not incomprehensibly alien. The same molecules appear, just in different proportions. The same physical processes operate, just under different conditions. It's comfortingly familiar while being intriguingly distinct. Exactly the kind of object that expands our understanding without overturning fundamental principles. This balance between familiar and foreign is perhaps the most important lesson from 3i ATLAS. The universe is vast, containing billions of star systems, each with its own history and its own collection of planets and comets and debris. But the same physics operates everywhere. The same chemistry governs molecular formation. The same gravitational dynamics control orbital motion. An interstellar comet from a star system billions of miles away is recognizable as a comet. We can study it with the same tools, interpret it with the same theories, understand it within the same framework we've developed from studying local comets. The universe has diversity, but also unity, variation built on common foundations. As October 2025 continues and perihelion approaches, the world's astronomers are watching 3i ATLAS with anticipation. This is the moment when comets typically show their most dramatic behavior, when outgassing peaks, when surprises happen. Whatever 3i ATLAS does in the coming weeks will be observed, documented, analyzed, and added to the growing understanding of this remarkable visitor from interstellar space. And then, gradually, the comet will fade, moving beyond our reach, leaving behind data and memories and scientific papers, and a slight expansion of human knowledge about the universe we inhabit. That's the story of 3i ATLAS. Not a story with a neat ending, but an ongoing scientific investigation into one of the rarest types of objects we can observe. A comet from another star system, passing briefly through our cosmic neighborhood, teaching us about conditions and processes light years away and billions of years ago. A messenger from the depths of space and time, carrying information encoded in ice and dust and molecules. A reminder that the universe is larger and stranger and more connected than our everyday experience suggests. That objects formed around distant stars can appear in our sky. That the galaxy is a dynamic place where material moves and mingles across vast distances. We're privileged to live in the era when humanity first developed the capability to detect and study interstellar visitors. A century ago, 3i ATLAS would have passed through unnoticed. A century from now, interstellar objects might be common targets, routinely observed and analyzed. Right now, in this transitional moment, each interstellar visitor is precious, rare, scientifically invaluable. 3i ATLAS is giving us that gift. That opportunity to learn and wonder, and expand our understanding. And we're making the most of it. Turning our best instruments toward this ancient wanderer, asking our deepest questions, preserving for future generations everything we can learn before it vanishes back into the darkness from which it came.